Hello learners, welcome to session 3 of NEET 5 Complex Numbers. I am Unkaila Dasmani, your course instructor. In the previous session, we established complex numbers can be added, divided, or subtracted. In this session 3, we are looking at geometry of complex numbers. By the end of this session, you should be able to define the modulus of a complex number, calculate the modulus of a complex number, and so define the argument of a complex number and calculate the argument of a complex number. The modulus for complex number. So the magnitude for a real number A is given by its absolute value, which may be described as the distance of the number from the origin. So this idea is easily standard to all complex numbers. So as you can see on the diagram, you can therefore find the distance that is called the modulus in this plane. So we can also find an angle between the positive y-axis and the light segment connecting to z. So we call that angle argument. Okay, so you can find the z here, the distance here. And by using the Pythagoras theorem approach, you can see that you can find the z. Because if I call here A and I call here B, or B, you can easily find the modulus of the z. So by the application of Pythagoras theorem, you can say that your z is a square plus b square. Okay, so you look at more of this in the next or subsequent pages. Let's look at definitions. For the modulus or absolute value of complex number z, that is a plus bi, is denoted by the modulus of z, as I've already said. So equivalently, the modulus of z is the length of the vector corresponding to the z. Z actually it represents a vector. Once you've been able to represent it in the coordinates, it's actually can be also be represented as a vector. The modulus of complex number may be calculated from its rectangular coordinates, and that is the real and imaginary parts using the Pythagoras theorem, as I've already stated. So if you have your z equals to a plus bi, then we can actually find our magnitude of z, or the same as the magnitude of a plus bi, and the same as square root of a square plus b square. And we are actually employing the idea of Pythagoras theorem. And also you note that the modulus of the conjugate of z is the same as the square root of a square plus minus b square. Okay, and I think get the same thing. So the modulus of its conjugate is the same as that is plus b square. So therefore we can say that the modulus of z conjugate is actually equal to the modulus of z. Okay, so that's very interesting. So you can actually look at for more example for that. For any complex number, you can have z square, or the modulus of z square is actually equals to z times its conjugate. Okay, so this one is so simple, and I think you can prove. If you want to prove this one, you can say that let's z equals to the usual one, a plus bi. So what do you get for z conjugate? A minus bi. So let's see, it means that the modulus of z square is actually equals to that is z times its conjugate, and don't forget the modulus of z square is actually equal to a square plus b square. That is from the modulus of z equals to square root of a squared plus b squared we've established earlier. Okay, if that's the case, then what can we see? Z dot z conjugate is actually equal to a plus bi, then you multiply by the a minus bi. Okay, so the conjugate is that, and by multiplication and simplification, simplifying this, don't forget keeping that I square is equals negative root 1 or negative 1 equals I square. So you simplify that, get a square plus b square. Okay, so you prove on that. So it's simple. For any complex number, another theorem, z square, that's the modulus of z square, is actually equals to z dot z conjugates. I think we've already talked about this theorem. Okay, let's see. For any complex numbers z and z1, you can actually prove that z1 dot z2, we take the magnitude or the modulus is the same as the modulus of z1 dot the modulus of z2. Okay, so this one is very simple, just extension of what you just proved. So go through and then find the proof. It is in your course material. Let's look at the arguments of complex numbers. The argument. So the modulus of complex number defines only its magnitude. We can also associate an angle to each non-zero complex number. So once we associate an angle, that becomes the argument. Let's look at this diagram. So the argument of the complex number z, that's the positive 1 here, that's the positive z, is denoted by the argument of z. I've talked about that. And the angle between the positive ray axis and the light segment connecting z to O. So from z to O is what we call, and it's also measured in the anti-clockwise direction. So you can see the angle here. You can also have the argument of negative z. Don't forget that. And that is also here. You can see pi plus pi. And the argument is here. Minus z is also here. Minus z is also here. So it's very, very, very interesting. So here we have so many things we can learn. Angles are measured in degrees or radians. You agree with me? So when I say 2 pi, you know it's equivalent to 360 degrees. 2 pi is actually equivalent to 360 degrees. I think you agree with me like that. So among the infinite many possible choices for the argument of z, we shall usually choose the only that lies between 0 and 2 pi. So in this course, that's what we are going to do. So for any complex number z, the argument z is only determined up to a multiple of 2 pi. And that is actually true. 2 pi equals 360 degrees. 2 pi equals 360 degrees. Okay. Let's look at some examples. So before we solve this example, let's look at the procedure we use. So by using the rectangular function or inverse tan function of some basic trigonometry. So the procedure is just to adjust the value of tan inverse of b on a, then according to the quadrants or the plane in which it lies. So don't forget about your quadrant. We have something first, second, 30. So Aquila, we're using some acronyms CAS. If you remember, C for cos, A for all, S for sine, T for tangent, for all. So the quadrants in which they lies are very, very important. So you have z equals to a plus bi. So the b and a determines the quadrant in which they lie. So when I have b to be positive, so I have a here. B to be positive, you can see, and a is positive. they all lies in the first quadrant. If A is negative, B is positive, A negative, B positive, you can see you can get something here. So it depends on the quadrant in which they lie. So if you forgot about your quadrant, just consult your curricula or any textbook of your choice. Go to online, every place, learn about the quadrants so that you can catch up here. So let's look at the few examples here. First one, we want to find the modulus and then the argument. So here I want to find the modulus, and the modulus is given by the modulus of u. I hope not forgetting about your approach we went through. We said that given as a squared plus b squared, and what do we get? You get 5. The square root of 25, square root of 25. Okay, let me clean it and write what square root of 25, and I get my 5. Okay, and you can see that since A is 3 is positive, B is also 4 positive, they all lies in the first quadrant. So the argument of u is actually equals to, you can find the tan inverse, or you can say the arctan. The arctan of 4 on 3, and what do I get? Arctan of 4 on 3, you get 0. Okay, so we find out that the argument of u was 0.9273, and the answer was in radians. Don't forget. So it implies that if you want degree, what do? We just multiply the result by pi 181 pi 9273, and what do I get? You get 53.13 degrees. Alright, so let's look at the b. The b was v equals to 12 minus 5i. So here the modulus of v equals to, so simple, the square root of 12 square plus minus 5 square. Great. So what do I get? You get 13. And then you go ahead, you can see that a is greater than 0 and b is less than 0. B is negative, a is positive. Therefore, where can you see the quadrant where v lies? B actually lies in the 4th quadrant. Once v lies in the 4th quadrant, you can say that the argument of v equals to 2 pi minus, or you can say plus, but if you say plus, then they are going to manipulate it again because it should be plus tan inverse, or you can say tan or tan inverse of minus 5 on 12, and that is same as 2 pi minus tan inverse of the absolute minus 5 on 12. So by doing that, approximately you get 5.8909. Okay, if you want the answer in degrees, what do? You multiply by 180 on pi. This one is in radians. Okay, it's in radians. So we will end here. We have a number of examples in your course material. Go through and solve them, and so don't forget to revise on your quadrants, the signs in the quadrants. Okay.